Hello, everyone. Welcome to this SimScale's webinar on how to get started with conjugate heat transfer analysis of compressible flows. I'm one of your presenters, Kanchan Garg. I'm a product manager here at SimScale, and I'm trained as an aerospace engineer with specialization in computational fluid dynamics. And my role here at SimScale is to develop our product roadmap and strategy for rotating machinery and flow control applications. And joining me today as a co-presenter is Jonas, who is a senior solution engineer and also has extensive background in CFD and numerical methods. And he has been with SimScale for about 2 years now. Before we proceed any further, I would like to let you all know that your mics are going to remain in mute. If you are facing any technical difficulty, please reach out to the organizers using the chat option. And throughout the webinar, please feel free to keep posting your questions in the questions panel. We'll try and answer them as much as we can during the webinar, and definitely at the end, we will try to have a couple of minutes or more, if possible, to answer your questions in a chat. Before we proceed, let's take a quick peek at how the webinar is structured. We will go through a very brief introduction to SimScale and SimScale's flagship solver Multipurpose, which is the one where we are going to demonstrate the conjugate heat transfer feature, specifically as applied to compressible flows. And this would be demoed using two industrial case studies, which is a hydrogen fuel tank filling and heat transfer in an automotive muffler. And as I said, we will try to wrap up such that we have a few minutes left over for Q&A at the end. For those of you who are new to SimScale, SimScale is the world's first truly fully cloud-native simulation platform that was founded as a company with the mission to bring simulation to every engineer, to make it accessible to every engineering team across the world without having any requirement for specific hardware or specific software licensing. This is made possible because SimScale is a web browser-based simulation tool. You can just simply go on to any web browser, and as long as you have a good internet connection, just log on to www.simscale.com, put in your login information, just like you would log into something like Netflix, and start simulating. And because we are web-based, it also means that real-time collaboration, just as the way Google Docs work, is possible. So you can work with your teammates irrespective of your geographical location. And most recently, we have also introduced a bunch of AI features, both on the workflow optimization side, as well as augmenting the physics-based or the PDE solvers. And some of this we will touch upon during the course of the webinar, so stay tuned. Getting a little bit into the topic, the solver that we are going to be demonstrating today is a proprietary CFD solver called Multipurpose. It is based on a binary tree-based measure, which is quite robust and able to handle quite complex geometries with very minimal cleanup. It is a finite volume-based RAND solver, and it has been very widely validated for industry applications, both internally at SimScale and by a lot of our customers, as you can see in the testimonials page on our website. And this solver, as far as compressible flow goes, is capable of handling both laminar, turbulent, transonic to supersonic flows up to around Mach 5. In terms of gas behavior, perfect gas as well as real gas analysis is possible, and we will see that today in the demonstration, including steady and transient analysis. Now, what's key about this solver is that generally when you talk about compressible flow analysis, it can be a bit tricky in terms of the numerous physics and thermodynamics involved. And from a CFD perspective, getting a converged result, a stable solution, can also require a lot of fine tuning. So we have worked a lot behind the scenes to make the multipurpose solver really robust in being able to handle multi-region geometries, multiple solids, fluids, and how the interfaces are handled, how boundary conditions and good initial conditions are handled, such that a very robust solution while being accurate also reduces the turnaround time. And as you can see through these colorful images, the topic of CHT and the topic of compressible flow definitely has a lot of applications across different uh, industries, such as turbomachinery, heat exchangers, HVAC, valves, and general industrial equipment. So in the interest of time, we have selected two such industrial use cases, which we're going to demonstrate next. And with that, I will hand over to Jonas, who will take us through the platform and is the real expert in showing you all the product features. Over to Jonas.
All right. So hello, everyone. Thanks for joining our session, and it's a pleasure to be with you today. As Kansan said, I'm a senior solution engineer with a team, and yeah, I'm here today to basically walk you through the two projects and, of course, help you learn more about our platform. So the first case study, we're actually going to study two cases today. The first one is going to be about the filling of a hydrogen tank, where we eventually want to optimize the filling time with respect to regulations. And secondly, we're going to see a different case of an automotive muffler, which is still a compressible case where high-speed air is going through at high temperatures. And with that, we can also see some AI features that are available in the platform, and we can generally see how the AI assistant in the platform can help you set up the case quickly. So let me now go back to the first case and jump in the platform real quick. So here I am. This is our platform. You just go to simscale.com in any web browser, and you log in with your username and password. So here I'm logged in, and all I do is go to my dashboard, where I can access all of my different simulation projects. So all of these projects are mine and are in the cloud with my SimScale account. And the cool thing about it is that apparently I don't have to have anything installed on my local computer. I just access all of my work by just the browser, as long as I have a stable internet connection. So let's start with the first one. It's this guy over here, the hydrogen tank filling project, where I just double click to open the project and land into the workbench, as we call it. Okay. So we are now into the project where we see different things. Apparently in the center, we got our geometry, and then here at the top left, this is where we start by uploading our geometry. So what I did over here is I uploaded a hydrogen tank geometry that consists of three main solids: the outer insulation, the supply pipe, and the liner, the internal layer between the insulation and the hydrogen. And I can quickly now take this geometry and prepare it for simulation. So I will quickly edit a copy. And the first thing I want to do is I want to extract the flow volume. So I can do that really easily by selecting the internal flow volume tool, picking one of the internal faces, and assigning the boundary face over there. And with a click of a button, I will have my internal flow volume generated. There you go. I got my flow region, which is necessary for the simulation. Furthermore, this is a case where it's symmetric. So I can, instead of simulating the full of it, I can just simulate just a quarter. So I can quickly split the geometry in a way that I just keep 1/4. So I can make a cut at the center, and I can make another cut to simplify things a bit. So this will make it a lot faster for me to simulate, since we're talking only about just 1/4 of the model. I can also get rid, for example, of this pipe. I don't need it. It's not too important for the simulation, so I just delete it. And I'm left with the flow region and the other two solids. Now I can save this model, and I can create a new simulation. Hitting the create simulation button, you see all the different options we have in SimScale. Today, we're talking about the multipurpose solver, but if you are interested in any other solver, feel free to ask in our chat or just watch other webinars relevant to the different solvers. For today, we are picking the multipurpose, which is really good for highly compressible fluids when we're also involving heat transfer between solids and fluids. So for that, I will just create a new simulation. And this will give me a new branch in the simulation tree. There you go. At this point, I can start setting it up. So at the top level, which is the global settings, I will just activate the conjugate heat transfer. And also the compressible toggle is activated. And then because we are talking about the transient phenomenon where we start the tank with a low pressure and we start ramping up the pressure in the tank through this little inlet over there, I need to study a transient phenomenon, right? So I will change the time dependency to transient. Next, and quite important, is the material. So for the material, I can create one fluid material. I click the plus button. I can pick hydrogen from the library. And I can assign hydrogen to the flow region by just selecting the relevant volume. We can use the perfect gas law for the equation of state, or we can switch to the real gas, depending on what we need. For the solids, we do the same. So we can assign aluminum to the internal liner here. And we can, of course, edit the properties accordingly. So imagine you can put here all the relevant properties that might be applicable to this specific material. And for the outer cell, we can quickly make a copy of this material, assign it to the outer cell, name it insulation, and change the properties to a different value that are representative of this material. And that's it. I'm pretty much okay with the material properties. And the next thing would be to set up the boundary conditions. So I click the plus button right there at the boundary conditions. And checking the different options, I know that I'm ramping up the pressure at the inlet to increase eventually the pressure in the tank. So for that, I will use a pressure inlet. I select the pressure inlet, simply assign it to the relevant phase, and here I can specify the pressure. It's a transient case, so I need to create a table for that. So maybe also changing the units to something more convenient. Let's do it bar. So at the start of the simulation, which is time 0, I start at, let's say, 1 bar. And at the end of the filling time, let's say it's after 60 seconds, I end up with a final pressure, which is 500 bar, for example. So this will create a linear evolution of the pressure at the inlet, replicating the actual ramping that's happening in the case of a tank filling application. The same I can do with the temperature, but for this case, I will just use a fixed temperature. Let's do minus 10 Celsius for this example. Also important, we don't have any outlets, right? It's a closed system. We just have an inlet. The only thing we need to do now is create a wall and specify the external conditions right there, selecting the 3 outer walls and setting them to convect the heat transfer with a default heat transfer coefficient and the ambient temperature. Since I'm doing a symmetry, I also need to create a symmetry by selecting all the symmetric sides of the model to tell the tool that, okay, this is just a quarter of the real model. Next, we have a very robust solver and smart default numerics that the user doesn't necessarily have to deal with the numerics actually. However, the numerics are all accessible. Theoretically, you don't need to change anything here. It works out of the box. And then on the simulation control, we just need to specify the total simulation time, let's say 60 seconds. We need to specify an appropriate time step for the simulation. And we also need to specify the writing frequency. That is how often we should print the results, and we chose to do it every 1 second. When it comes to number of processors, since we're on the cloud, you can literally just start the simulation on a 192 core machine, or of course pick between smaller machines that might be a bit more efficient for smaller cases. So by default, you don't have to worry about that. We just advise you to pick the automatic setting, which let us pick the best machine for your simulation. However, you can always bypass and select whatever machine you might like. Finally, I might want to create some result control items, for example, like a probe point somewhere in the tank to monitor the temperature, or an area average at the inlet, for example. With this tool, I will be able to monitor, for example, the mass flow rate at the inlet and the temperature at this location, or I might want to add more points eventually to use them as probes. Lastly, before we start the simulation, we can check a bit about the mesh. We have a unique way of meshing. We have a pretty automated algorithm in the background that basically, with just the minimum input from the user, just using the slider here from left to right to dictate the fineness, we just build an automatic mesh that fits really well in most of the applications. Of course, for a bit more advanced users, you can always go and select manual meshing and specify exactly what sizing you might need. And you can even add refinement zones in the tank, like, for example, like a cylinder. You can place the cylinder right there. In case, for example, you want to refine the mesh only near the inlet region. Having done all that, I can now go ahead and start a new simulation. That's it, my simulation is on the cloud. And let's go now check an already finished example, which is, by the way, it's gonna be a public project, so you can access all of you later and check the setup on your own. Now, this is a pre-set up model, which we already simulated with all the relevant conditions. In this case, we used real gas law for the hydrogen. We used a transient pressure inlet and with a varying temperature as well, with inputting a full table of data. And we have done a pretty good work on the mesh by creating multiple refinement regions to refine the mesh only where it's necessary. This is my simulation. We ran it for 35 seconds, and we can easily take a look at the results by post-processing. So whenever you see a green check mark next to the run, it means that the run is done, and you can post-process the results. So the results are now loaded to the online post-processor, and I can do here all the post-processing I need. For example, I'm now checking the temperature at the final time, which in this case is just 37 seconds. We can move this a bit earlier. Let's see what happens at 15 seconds, for example. We get a slightly different temperature distribution in the tank. I can easily change that to velocity, so we understand what's happening here. If I want to check what's the peak velocity here, I can inspect and see that the velocity here is roughly 87 meters per second. Of course, I can do other cool stuff like creating particle traces to see how the jet of the flow will hit the backside of the tank. And of course, also animate it to create nice visualization for my presentation. All right, so that's what I wanted to show for this first case. I think it's really interesting. Like in just 10 minutes, we were able to set up and start our first simulation with minimum user input and quite intuitive workflow. Now let's jump to the second case, which is the muffler. You see I have a project next to my tank project where it's a muffler. And the idea is exactly the same. We start with the geometry. And we can start populating a new simulation. In this case, this geometry is a bit more complex as it contains the flow region, but also contains multiple other components like internal plates, pipes, etc. I think it's a bit more clear if we see it in transparent mode, where we can see the higher complexity of this model with several openings and pipes that are inside. So I can easily just create a new simulation and use again the multipurpose and start filling in the setup. Or this case, I want to show you something else, our actual AI assistant, which is over there. So I can basically open the AI assistant and ask any question I want. For example, I can ask it to help me to optimize my design. So to save some time, I have actually done exactly that before the call and in a pre-recorded video. So let's go through this really quick to make things a bit more efficient. So I will just play the video for you and I will explain all the steps. So we have our project and we ask our AI assistant to help us optimize the design. The AI assistant will come with some suggestions of what type of simulations we can do, but we can always add user input and refine, saying, I want to do heat transfer between fluids and solids. So then it can come up with the appropriate suggestion. Perfect. So then I can ask it, okay, let's do a conjugate heat transfer analysis with a multipurpose solver. And the AI assistant, you see, it just generated one simulation for me on the left. Now it asks me about the material. So I can say, okay, please assign air material to the flow region. And the assistant will just find the flow region and will automatically assign the material, the right material to that. Next, let's say I want to assign the material to the solids, but I don't know what material to use. I can ask it a question. For example, can you suggest what are the material that I need for the muffler? And it will come up with some suggestion. It says you can use either steel or aluminum. That's the common ones. And then I can say, okay, let's use steel for the solids then. And the assistant will automatically select all the solids and will assign steel. All this is done automatically. My mouse is basically here, right? I'm not doing anything. It's done automatically via our AI assistant and API integration. Now, about the boundary conditions, we ask it to create a velocity inlet. Let's use 30 meters per second in the Z direction, and let's use a certain temperature for that. Okay, it tries to do it and it succeeds. We have our velocity inlet assigned on the inlet region, and then we can do the same for the pressure outlet. So this is a different case where we have both an inlet and an outlet, so we need to create also an outlet. And this is exactly what I asked the tool to do. We create the pressure outlet. And of course, it's still an assistant, right? It's not as smart as a human being, so it might forget something. So we say, okay, we forget the walls. Can you please assign the walls to me, for me? And then it assigns the wall. I can select one of the different options, and then I can ask it for recommendations. For example, what is the typical heat transfer coefficient that I should use in this case? And what is the typical ambient temperature conditions that I should use? So I can feed this information in the chat. And it will come with some recommendation. And then I can apply this recommendation to the setup. There you go. So yeah, it updated the boundary condition. And moving next, apparently I want to monitor some quantities in the domain. So I want to create some area average controls like we did in the case of the tank before. So I asked it, can you please create surface average controls at the inlet and the outlet? And this will now automatically do it for me. So imagine you have multiple surfaces, you want to create result controls. This saves you a lot of time because it can automatically create multiple controls with just a prompt. Before simulating, we can discuss a bit about meshing. Imagine I'm a new user, so I don't know what to use there. I can ask a question, and it can guide me to the right documentation where I can read about the meshing requirements. And it can propose some settings. So I can say, okay, that's really good. Let's use medium fineness, for example, to start with. And it can update the fineness for me. And now it's ready to start the simulation. So let's start a new round, please. It will find some warnings that might happen on the setup, will warn me about those. And then I have, of course, the final decision to make. Okay, let's move ahead. Let's proceed with the simulation. And you see, it started a simulation. Now I can say, for example, okay, thanks. Can we do another simulation? Can you change the temperature at the inlet and start another one? And of course, it can help. So I just feed the prompt. It will update the temperature. You can see here, and it can start another simulation. That's it. So we just saw in the second case with just text interaction how we were able to set up the same case of this muffler that we set up here, and the AI assistant it helped us with. So imagine this AI assistant can be applied to anything, right? You can ask it anything you want, even request for support on different errors that you might see in the platform. But of course, you also get real support from humans by opening the chat, right? So when you are a customer of SimScale, you have access to our dedicated customer success and support engineers, where they can help you via the chat box here by sharing your project with us. You can ask us any question, and we can come back to you within a few minutes with help. But sometimes it might be more helpful and faster if you just ask the assistant, which is waiting. So now my simulation is done. The simulation was run before, and it took just about 20 minutes to simulate, and we can post-process the results on this model as well. There you go. So my results are loaded. I can color everything by temperature, for example, so I can see the temperature evolution on my component. Maybe I can make a cut plane through the center to check the velocity inside. Okay, I can maybe color that by temperature. I can also visualize the mesh if I want. And of course, I can do other nice stuff like maybe creating some streamlines. Or save screenshots and animations. Like we did here. All right, that was basically it for today. I hope you enjoyed the live demonstration. If I am to summarize what we discussed, going back to the slides. So today we just made a technical overview of our multipurpose analysis setup and capabilities, focusing on the conjugate heat transfer applications by taking two real cases of a hydrogen tank filling and of an automotive muffler with heat transfer. We saw best practices on how to prepare the geometry for simulation, how to prepare the mesh with relevant refinement zones or manual or automatic sizing. We saw the different boundary conditions and different solver configurations that are applicable for compressible flows with our new multipurpose conjugate heat transfer mode. Finally, we saw how, with the help of the AI assistant, we were able to get help on the setup. So if we were new users, we could easily utilize the help taken from there to help us set up our first simulation with minimum effort and confidence. Now we can move on to the last section of the session. So we can take any of your questions and try to answer. I think for that we need to I need to give it back to Kansan, that has the control of the questions.
You can keep sharing your screen, Eunice, and I do have some questions coming on. And first of all, it's a wonderful presentation, Eunice. I mean, I have been playing around with the AI assistant too, and it is just incredible that I can type in things and have the AI assistant figure out a lot of things like material properties and everything that I do not know of off the top of my head. So the first question is actually on the multipurpose solver, whether this is available on the community. To answer that, I think I can quickly take that. So multipurpose solver is one of our proprietary solvers, and therefore not available on the community model. If you want to get started with similar applications, you can try some of our other solvers. But for accessing multipurpose specifically, where you have a bunch of other features like multi-phase, multi-species, real gas analysis, cavitation, everything, the best thing would be to get in touch with our sales team at this email that you see here on the screen, and we can set up a trial for you to just try your hands at this. The next question, I believe, would be you would be better positioned to answer that, Eunice, given the recent simulations that you've done in CHT, is what would be like the typical cost? And I believe this is in terms of core hours of running a CHT simulation, like say for a heat exchanger or maybe.
Okay. Yeah, so we can take a look at this one actually. This one took just 23 minutes and it consumed only 6 core hours. But this is a quick case we used for this demonstration. The mesh is a bit coarser than ideal. So maybe for a finer mesh, this might take a bit longer, or you might need to use a larger computer. Generally, the idea of core hours is calculated by the size of the computer you're using and how long it's running. So imagine if you run a simulation on a 16-core machine and it takes 1 hour, this will consume 16 hours. So in this case, this ran on a 16-core machine, but it just ran for about 23 minutes. That's why it only consumed only 6 core hours. So with just 6 core hours, we can get a quick result, but maybe for a more accurate result with a finer mesh, etc., you might need, I would guess, right, for similar applications, like up to 20 to 30 core hours to be on the more safe side.
Okay, thanks, Janice. And another question on the setup itself for a CHT problem is whether there can be more than one solid region in one simulation, and generally what
Exactly.
solid materials would be available.
Yeah, so with our multi-purpose CHT solver, you can have multiple solids. So you can see here, this model contains, I don't know, roughly 10 different solids. In this case, all of them are assigned to steel, but you can easily pick from the material available from the material library we have here. You can pick any material you want and bring it in the simulation. And you can also, of course, create your custom material by making copies of this material and store them to your own material library to utilize later.
Great. And just a final question. Which plants is the AI assistant available for? Do you want to take that, Eunice?
I'm not entirely sure which plans is it coming with. If you have any inquiries, you need to check with our sales team. I think we can always activate it for a trial, and then we can discuss how we can apply it to your organization. I think that
just
helps.
Yeah, I think I would say the same too, right? Because this is something that we have recently launched.
Exactly.
So this is more on a sales request basis right now. So I would again say, please get in touch with our sales team, and someone would set up a call
Exactly.
and a demo. What is the
Exactly.
accuracy rate from creation to actual as built operation? Uh, I am assuming this is a question around the accuracy of the solver. If not, then please let me know. Typically, we have observed or we have validated the solver up anywhere between 2 to 5% of accuracy with test data. And for example, like a transonic compressor generating the full performance map lands us like below 5% of actual test data. Well, I think we are about 6 minutes over time. So let's wrap up. And thank you everyone for joining this webinar. It's been wonderful being able to bring all of these new features and new product releases to you. If you have any questions that we have not been able to get to or you would like to follow up on, please feel free to reach out on the email IDs provided or directly to our sales contact. Once again, thank you for joining and have a very good rest of the day.
Thank you, everyone.